We present adaptive rigidification of discrete shells. This follows work on adaptive rigidification of elastic solids, where regions with zero strain rate become rigid, and return to elastic as needed. Shells feature two distinct types of deformation: the planar and bending deformations. Planar deformation can be monitored using the membrane strain rate, while bending deformation requires a separate metric. In our paper we propose a scale-independent metric for bending rate. Our adaptive rigidification algorithm is consistent across resolutions. This excludes the differences inherent to the changes in resolutions such as numerical damping. As rigidification thresholds relate to speed limits, a single choice of threshold can work well for different material properties. In this example, local deformations of a sleeve require elastic deformation during bending at the elbow, while large non-deforming portions of the rest of the sleeve can be simulated as rigid bodies. This permits computation to be an order of magnitude faster than a fully elastic simulation. The sleeve elastifies as needed at the elbow, but likewise, the wrinkles can simulate as a single rigid body during rigid motion. To our knowledge, no other reduction technique can completely coarsen highly bent regions. Mixing rigid bodies with elastic elements increases the mass ratio, leading to poorly conditioned systems during implicit integration. This is not a problem for direct solvers, and is likewise easily resolved with Jacobi preconditioning. However, nonlinear elastic materials undergoing large deformations can also exhibit poor conditioning. This example does this by mixing large and small deformations, and we note that the condition number in this example is actually improved through rigidification. Strain limits can also cause conditioning issues by raising the stiffness ratio. In the case of a rigidifying system, it instead increases the rates of rigidification, further improving the computation time. In the previous work on adaptive rigidification, an oracle identifies elastification. For shells, this oracle does not work well on first contact. We instead present different techniques to improve elastification at new contacts. See how these remain visually consistent with the elastic reference model. Pulling on a tablecloth exposes a large non-deforming region ready for rigidification. See how the bottle contacts create a local elastification region around it where the tablecloth can stretch. This enables some steps to compute one order of magnitude faster. Here is a toy dancer with a plastic crinolet-like dress. That dress remains mostly rigidified as it moves around, but features elastification when needed. The simulation steps are often 1 to 2 orders of magnitude faster than the elastic simulation. This fighter has a loose sleeve. Here is a rotating sphere near a frostum, folding the cloth.